let's see. So we had the reciprocal identities, we have the quotient identities. All right, and I think that was where we left off, actually. So we were going to do an example, right? So here we had an example where we just suppose that theta is an angle in a right triangle, and we were told that sine of theta is equal to 1 over the square root of 5. And then we found the values of the other trigonometric functions of theta using trigonometric identities and whatever, right? So I think actually the way that I did this was I actually just, just drew a right triangle that represents that equation. Right? I know that sine of theta is supposed to be 1 over the square root of 5. So I constructed a triangle where I had an angle theta such that sine of theta would be square root of 5 over 5, basically, right? Yeah. So that's how I got this figure over here, right? The opposite over hypotenuse has to be square root of 5 over 5, right? And then using that, I was able to find the third side by Pythagorean theorem. It's 2 square root of 5. And then now that I have all three sides of the triangle, it was very easy to find what sine and cosine and tangent and so on were, right? So just as a brief recap of that last example we went through. Any questions on that, by the way? Any questions at all? No? All right, good. So you'll definitely see a problem like that on the test, right? So now that I have that, let's get back into section 5.2 here. All right. So there are more trigonometric identities I want to go through. Let me see if I want to do another example first before we go on to that stuff. So we already did the special angles. Good. All right. Yeah, let's do another example, kind of similar to this one. Okay. So in this example, let's suppose we have, I think I write better when this is flat on the table here. So let's see. Suppose theta is an angle in a right triangle, and that tangent of theta is equal to square root of 5. Okay. Find the values of the other 5 trigonometric functions. Find the values of the trigonometric functions of theta. Trig functions of theta. Okay, fair enough. Okay, so let's see. We can do some of this with trigonometric identities, right? Oh, we don't have the Pythagorean identities yet. Never mind. Yeah, so instead of doing that, let's go ahead and draw a triangle first. Okay, so I'm going to draw a triangle where tangent of theta is equal to square root of 5, right? So if you recall, if we have tangent of theta, right? Tangent of theta in a right triangle is always supposed to be equal to opposite over adjacent, right? So we need that to be equal to square root of 5, which is the same thing as square root of 5 divided by 1, right? You can divide anything by 1 without changing it, right? But now we have a numerator and a denominator, right? So we can set the opposite side to be equal to square root of 5 and the adjacent side to be equal to 1 now, if we write it as a fraction like that, right? Okay. So strategies, right? Now, make a right triangle. Doesn't have to be to scale. Make one of your angles theta. And then now tangent of theta is opposite over adjacent. So we need the opposite side to be length square root of 5. We need the adjacent side to be length 1. Okay. Yeah. I think I'll pause here for a second, right? Because, judging by the active engagement assignment too, like some of you might be having trouble like generating this kind of triangle. So I want to pause here, make sure there are no questions on it. Yeah. All right, we're all good with that? All right, good. All right, so then now we need the third side, right? But that's just Pythagorean theorem, right? We know, I'll call this A, right? I'll call this B, right? And I'll call the missing side the hypotenuse C, right? So A squared plus B squared is going to be equal to C squared. I'll plug in my AB and find my C, right? So I have 1 squared plus square root of 5 squared is equal to C squared, right? All right, but 1 squared is just 1. The square root of 5 squared just undoes the square root, so we just have 5, all right? Okay, and so now we have 6 is equal to C squared. We can take the square root on the top and on both sides of the equation, I mean. So right, you're going to get plus or minus the square root of 6 is equal to C, right? You remember you could get a positive number or a negative number. But then, right, since we're dealing with side lengths in a triangle, we can only have positive side lengths. So C is just the positive square root of 6, right? Yeah, fair enough. So now I have the whole triangle filled out, basically. Okay. All right, so let's compute sine of theta and cosine of theta and so on and so forth. Sine of theta is supposed to be opposite over hypotenuse, so that's going to be equal to square root of 5 divided by square root of 6, right? But then now we're going to rationalize this, right? So I guess I'll do it the same way I had been doing it here, right? We're going to multiply by, come on, yeah, we're going to multiply by square root of 6 to rationalize that denominator. But we can't just multiply the denominator by square root of 6. We also have to multiply the numerator by square root of 6 in order to preserve equality, right? We can only multiply things by 1 or else we'll change their value. Square root of 6 over square root of 6 is just a fancy way of writing 1, right? Okay. But now we can simplify here, right? So we have square root of 5 times square root of 6, which is the same thing as square root of 30. And it can't be simplified any, right? The prime factors are 2, 5, and 3, right? So there's no perfect squares to pull out. So square root of 6 times square root of 6 is just 6 downstairs. So square root of 30 over 6. That's our sine of theta. Okay. Any questions on that? Any questions at all? Okay. Let's do cosine of theta then. Okay. So that's adjacent over hypotenuse. So we have 1 over the square root of 6, right? I'm going to do the same trick here. Maybe I won't use that light blue color anymore. Let's make that a dark blue color so it's easier to see. Right? So times square root of 6 over square root of 6, right? So up top we have 1 times the square root of 6. We're just going to get square root of 6. Down on the bottom, square root of 6 times square root of 6 is 6. So then there's my cosine of theta. Yeah. If I'm going too fast, let me know. Yeah, if you have any questions at all, raise your hands or just shout out, a question. That's fine too. All right, tangent of theta, opposite over adjacent. So it's going to be the opposite side over the adjacent side, which is equal to square root of 5. But of course, we knew that already. That was given to us at the very start of the problem in the problem statement itself. That tangent of theta is square root of 5, right? That's how we were able to generate the triangle. Yeah. Okay. Now we're going to do cosecant of theta. Remember, that is the reciprocal of sine. So that would be equal to the square root of 6 over the square root of 5 instead, right? Here, I'm taking the reciprocal of this right here. Okay. So now we rationalize it, right? I guess I should use a different color. Here we go. So we rationalize it. So we're going to multiply square root of 5 on the bottom, but we also have to multiply by square root of 5 on the top, right? And so this is going to be equal to the square root of 30 upstairs again. But downstairs now, it's going to be divided by 5 instead of 6, okay? Secant of theta. Remember, that's just a reciprocal of cosine. Cosine's 1 over the square root of 6. So then this will be the square root of 6 over 1, which is just square root of 6, right? Yeah. And cotangent of theta is a reciprocal of tangent. So I'm going to get 1 over the square root of 5, right? I'm going to rationalize it by multiplying by square root of 5 over square root of 5, right? So we're going to get that this is square root of 5 upstairs. Downstairs is just 5. Okay. And there we have it. All right. So any questions on that at all? Any questions on that? All right. So I'm glad we did that problem because now we're going to talk about the Pythagorean identities. Okay. So we did the reciprocal identities. We did the quotient identities, right? Now we're doing these Pythagorean identities. So Pythagorean identities. All right. So let's do some justification for this. Okay. So we have an angle theta here, let's say, right? This is, of course, the opposite side. This is, of course, the adjacent side, right? This is, of course, the hypotenuse. Let's call them A and B and C again, right? Okay. So according to the Pythagorean theorem, right? According to the Pythagorean theorem, I have A squared plus B squared is equal to C squared, right? I'm going to divide both sides by C squared now. Okay. So I'm going to take this whole left-hand side, divide by C squared. Take this whole right-hand side, divide by C squared. Okay. Now division distributes over addition, right? So this is the same thing as A squared over C squared plus B squared over C squared, right? And C squared over C squared is, of course, equal to 1, right? Everybody okay with that? Yes. Why am I doing this? I'm going to justify the Pythagorean identities, why they're true, before I state them. Yeah. Okay. All right. Now, A squared over C squared, that's really the same thing as A over C, quantity squared. Same thing with B squared over C squared, that's B over C, entire quantity squared, and that's going to be equal to 1. Okay. Now, I'm almost done here. So, if I look at my angle theta over here, sine of theta, which is equal to opposite over hypotenuse, that's the same thing as B over C. And cosine of theta, which is equal to adjacent over hypotenuse, that's the same thing as A over C. And so what we have here from this equation is, well, A over C is the same thing as cosine of theta. So this is just cosine of theta, quantity squared. B over C over here, that's sine of theta, entire quantity squared, and that's equal to 1, right? Just by doing those substitutions, right? So this went over here, right? And this went over here, right? Okay. Any questions on that? Oh, yeah. Oh, I haven't written down the Pythagorean identities yet. I'm just doing my justification first. Yeah, I'll write down the Pythagorean identities in just a second. Yeah. All right. So now, cosine of theta, that quantity squared, we have a shorthand notation for that, right, that we use in mathematics. It's not exactly a good one for algebra reasons, but we call it cosine squared of theta instead. Okay. Same thing with sine of theta squared. We call that sine squared of theta instead. Okay. So we have cosine squared of theta plus sine squared of theta is equal to 1. Okay. Now, this triangle that I drew is completely arbitrary, right? So this formula works for every single theta that's an acute angle and a right triangle. So for every single acute angle, you plug it in, cosine squared of theta plus sine squared of theta is always equal to 1. Yeah, always, for every single angle theta. Okay, which is kind of interesting. It's so interesting, in fact, that we're going to give it a name, and it's called the Pythagorean identity. So the Pythagorean identity goes like this. Sine squared of theta plus cosine squared of theta is equal to 1. Okay, fair enough. So that's your first Pythagorean identity there. And it's called a Pythagorean identity, obviously, because we use the Pythagorean theorem to prove it, right? So any questions on that? Any questions at all on that? All right. Now, your next Pythagorean identity is you take this equation here, sine squared of theta plus cosine squared of theta is equal to 1. Right, so I'll rewrite it over here. Okay, so I have sine squared of theta plus cosine squared of theta is equal to 1. And then now, I'm going to divide both sides of the equation by cosine squared of theta. Okay, which of course I can only do if cosine of theta is not equal to 0, right? Can't divide by 0, right? So this is only going to work for angles where cosine of theta is not equal to 0, right? But we don't need to worry about that because we're in a right triangle right now. Cosine of theta will never be equal to 0, okay? Your adjacent side will never be equal to 0 in a triangle, right? So cosine of theta will never be 0. So that's kind of nice. Okay, now I'm going to distribute this, right? Because division distributes over addition. So we have that sine squared of theta over cosine squared of theta. plus, well, cosine squared of theta over cosine squared of theta is just going to be 1. They cancel off. And then we have 1 over cosine squared of theta, right? Which I'm going to rewrite as 1 over cosine of theta quantity squared. Okay. I can do that. Okay. In fact, I can do the same thing on the left over here. That's the same thing as sine of theta over cosine of theta squared. Okay. There we go. Any questions on that so far? All right. Well, sine of theta over cosine of theta, we have a quotient identity for that, right? A quotient identity says that tangent of theta is the same thing as sine of theta over cosine of theta. So this is really just tangent of theta that's being squared here. We have a reciprocal identity for this. 1 over cosine of theta is the same thing as secant of theta. So we have tangent of theta quantity squared plus 1 is equal to secant of theta quantity squared, right? And we use our shorthand notation now, and we get that tangent squared of theta plus 1 is equal to secant squared of theta, which is your second Pythagorean identity there. And it's usually written as 1 plus tangent squared of theta equals secant squared of theta. But of course, addition's commutative, so it doesn't really matter which comes first, right? All right. So keep in mind, I got that from the very first equation here, right? Just by dividing both sides by cosine squared of theta, right? If I had instead divided by sine squared of theta, you could also prove that 1 plus cotangent squared of theta is equal to cosecant squared of theta. Exactly the same steps, just using the other quotient identity, right? The other reciprocal identity, that's it. Okay. So these are your Pythagorean identities. Okay. So any questions on that? Any questions on that? All right. Well, if we have that, then now let's go back to that last example we just did, right? So that last example, right, we had this theta was an angle in a right triangle, and we were told that tangent of theta is equal to square root of 5. Find the other 5. Find the other trig functions of theta. Trig functions of theta, right? And that was the instructions, right? And we drew a triangle to find it, right? Okay. Yeah, now I'm going to do it purely with trigonometric identities, okay? Just with trigonometric identities. So, start off with tangent of theta is equal to square root of 5, right? All right, let's find out what cotangent of theta is, okay? I'm going to use my reciprocal identity, right? Reciprocal, right? Tangent of theta is the same thing as 1 over cotangent of theta. All right, so 1 over the cotangent of theta is equal to square root of 5, right? Now, if I have that this fraction is equal to this, then if I take reciprocals on both sides of the equation, I'll get that cotangent of theta is equal to 1 over the square root of 5, right? The reciprocal of the left-hand side is equal to the reciprocal of the right-hand side, right? So I just took reciprocal on the left-hand side and on the right-hand side. Yes. So tangent of theta is the same thing as 1 over cotangent of theta. I used the reciprocal identity there. I didn't actually take a reciprocal at all. Yeah, okay. Yeah, so I'm using my reciprocal identity. Yeah, yeah. Here's where I actually took the reciprocals on both sides of the equation, right? Yeah. To simplify this. Let me write that a little bit neater here. Maybe. This thing's pretty slow to respond here. This says cotangent of theta. Okay. And on the right-hand side, we have 1 over the square root of 5. Right? Mm-hmm. That's fine. Yeah, that's perfectly fine. This step right here is completely unnecessary. Yeah, okay. Yeah, that's fine. But now, of course, we have to simplify it, right? So we're going to multiply by square root of 5 over the square root of 5, right? And we're going to get that this is square root of 5 upstairs and 5 downstairs, right? So there's your cotangent of theta, right? Okay. Any questions on that? Any questions at all? Okay, great. So that's two of our trigonometric functions we know so far, right? We still got to get sine, cosine, and cosecant and secant, right? Still got to get all those. So here's what I'm going to do. I'm going to use a Pythagorean identity. Okay. Now, there's a tangent Pythagorean identity, right? And I'll go ahead and scroll up since we have it right there. Right? 1 plus tangent squared of theta is the same thing as secant squared of theta. So I'm going to start off there. I'm going to write that equation down. Okay. So 1 plus tangent squared of theta is equal to secant squared of theta, right? So this is my Pythagorean identity, right? Pythagorean identity. Okay. All right. So I can do that, no problem. Now, I know that tangent squared of theta is the same thing as tangent of theta, quantity squared, right? But I already know what tangent of theta is. It's just the square root of 5. So this will just be the square root of 5 quantity squared. Okay. There we have it. Any questions on that? All right, a little bit of algebra there, just replacing things with they're equal to, right? Yeah. I kind of skipped a step there. Let me put that step back in there. So tangent squared of theta is a shorthand notation for this. So when I write tangent squared of theta, what I really mean is tangent of theta, that whole quantity squared. Yeah. And so to get the next line there, all I did was I said, well, tangent of theta is the square root of 5. Okay. So all I did was just replace tangent of theta with what it's equal to. Yeah. So that's how I got that line in particular. Maybe you were jumping ahead a little bit. Square root of 5 squared is indeed 5. Yeah. So you can go ahead and skip to that step. Yeah. Yeah. So that's fine. Okay. So then now I simplify. I get 1 plus 5 equals secant squared of theta. Right. So 6 is equal to secant squared of theta. Okay. So that's what secant squared of theta is equal to. Okay. Now I got to find out what secant of theta is equal to, right? So I got to take the square root on both sides of the equation. So I get plus or minus the square root of 6 is equal to secant of theta. But we're talking about a right triangle here where all of our side lengths are positive. So then we have to have that the secant of theta is a positive number, right? So, so I'll get rid of that. I get the secant of theta is equal to square root of 6. Okay. Fair enough. So any questions on that? Any questions on that at all? All right, so now I have that tangent of theta is the square root of 5. I have that cotangent of theta is the square root of 5 over 5. And I have that secant of theta is square root of 6. Okay, so that's 3 of my functions, right? So I need 3 more, right? Okay. So next, if I know what secant of theta is, then it's really easy to find out what cosine of theta is. Okay, so I'm going to use my reciprocal identity here, right? So secant of theta is equal to square root of 6, right? But secant of theta is the same thing as 1 over cosine of theta. Okay, so here I've used my reciprocal identity to say that secant of theta is equal to 1 over cosine of theta, right? Now I can take reciprocals on both sides of the equation to get that cosine of theta will just be 1 over the square root of 6, which I can then rationalize. All right, so I get that this is square root of 6 divided by 6. Okay, so now I have my cosine of theta. Okay. Any questions on that? Yes. Well, you always have to. Let's see. Hmm. You could have done a quotient identity. It would have been a lot more complicated, I feel like. But tangent of theta is sine of theta over cosine of theta. So then you could have said, well, sine of theta divided by cosine of theta would be equal to square root of 5. And then you could have come up with some equation involving sine and cosine and maybe found out what it's equal to then. I think it's a lot easier to use a reciprocal identity. Yeah, okay. But yeah, no. In general, yeah, when you're doing these problems, there are probably like multiple ways of solving them. Yeah. So if I find that you do a different way that is equivalent to what I did, then that's perfectly fine with me. Yeah. Okay. As long as you represent your work in a clear manner. Yeah. Okay. All right. So I have cosine of theta. Let's find out what sine of theta is using, again, a Pythagorean identity. Okay. So Pythagorean identity. Okay. We have sine squared of theta plus cosine squared of theta, right, is equal to 1, right? My Pythagorean identity there. So I know that cosine of theta is 1 over the square root of 6, essentially. So then cosine squared of theta will be equal to 1/6, right? Just by squaring this, I get 1/6. Okay. You also could have used this. Square root of 6 squared is 6. 6 squared is 36. 6 over 36 is 1/6, right? Okay. So I have sine squared of theta plus 1/6 is equal to 1. Okay. Any questions on that? Now I'll subtract 1/6 on both sides of the equation there, and I get sine squared of theta is, well, 1 minus 1/6, right? That's 6 over 6 minus 1 over 6, which is 5 over 6. Okay. Now I can take square roots on both sides, and I get that sine of theta will be equal to the square root of 5/6, really plus or minus, but we're talking about lengths in a triangle, so it's going to be a positive square root of 5 over 6, right? I have to rationalize that. Can't just leave it like that. This is the same thing as square root of 5 over square root of 6, right? Now I can multiply by square root of 6 over square root of 6 on the top and the bottom, and I get that this is equal to square root of 30 divided by 6. Okay, that's my sine of theta there. Okay. Any questions on that? Right. Now let's do my cosecant of theta, right? So cosecant of theta is just 1 over sine of theta, right? This is my reciprocal identity. Reciprocal identity, right? So then now, well, sine of theta is square root of 5 over square root of 6. So this should be equal to the reciprocal of that, which would be equal to square root of 6 over the square root of 5, right? And so now I can say, well, I need to rationalize that denominator. So I'm going to multiply by square root of 5 on the top and the bottom, and I'll get that this is square root of 30 over 5, okay? All right, so I found the values of my 6 trigonometric functions. Yeah. Okay. Any questions on that? Hopefully they're the same values we found above doing the exact same example. Yeah. Okay. One of them with the triangle, one of them with the identities. All right. I just wanted to show you that you do get the same thing using the identities. Okay. All right. Any questions? Okay. So let's talk a little bit about complements of angles, right? So, this is a definition that I've probably already given you. Right? I'll call this subsection trigonometric functions and complements. Okay, complements there. Okay. So this is a definition that I've probably already given you, but just in case, right? Two angles are said to be complementary. Let's give them names, actually. How about we say alpha and beta? Two angles, let's say alpha and beta, are said to be complementary. Complementary. If they add up to be 90 degrees, right? Or pi over 2 rads. Fair enough. All right. So if we look at a right triangle, right, we have a right angle over here. We have an angle theta over here, right? And so we know this all has to add up to be 180 degrees. So then this angle right over here, right? This angle always has to be equal to the complement of theta. So always has to be equal to 90 degrees minus theta. And there's no choice for that, right? All three angles have to add up to be 180 degrees, so that forces our hand there. So we'll always have that theta and this angle are complements of each other. Okay. Any questions on that? So I'm going to look at two different labelings of this triangle then. So I'll kind of blow it up a little bit here. Same triangle. Right. Give myself some space though. So here's my theta. Right. Here's my 90 degrees minus theta. Wait, I'll do that in purple. Thank you. Oh. All right. So in purple over here, we have 90 degrees minus theta. Okay. Good. So in black, I'm going to label my opposite, adjacent, and hypotenuse for theta here. So this is the opposite side for theta, right? This is the adjacent side for theta. This is the hypotenuse for theta, right? And in purple, I'm going to label my opposite, adjacent, and hypotenuse for 90 degrees minus theta. So this will be the opposite side of 90 degrees minus theta. This would be the adjacent side for 90 degrees minus theta. Hypotenuse is still hypotenuse. That's nice. Okay. So if I look at sine of theta, right? Okay. If I look at sine of theta, right? Say this side length is, a side length of length A. This is of length B, and this is of length C, right? Well, sine of theta is supposed to be opposite over hypotenuse. So that would just be equal to B over C. Looking at this triangle, right? B divided by C. Okay. But if I look at cosine of 90 degrees minus theta, okay, all right, well, that would just be adjacent over hypotenuse, but the adjacent side of 90 degrees minus theta is B. The hypotenuse is still C, right? So I have that sine of theta is the same thing as cosine of 90 degrees minus theta in a right triangle. Yeah, fair enough. So sine of theta is the same thing as cosine of the complement of theta. Yeah. And so that's actually why cosine is called cosine. It's a co-function for sine. It means that it's a function of the complementary angle. Yeah, we get the same value. So sine of theta is equal to cosine of 90 degrees minus theta. Okay, so let's make a little definition here. Do I want to make a definition? Nah, that's fine. Let's just go through my co-function identities. Save some time here. So these are called co-functions because they involve the complement of theta. Okay. So here's your co-function identities. We just showed this one. Sine of theta is cosine of 90 degrees minus theta, right? And you can phrase it in terms of radians also. It's pi over 2 rads minus theta, right? Okay. Cosine of theta, right, is equal to sine of 90 degrees minus theta. They are co-functions of each other. Yeah. Okay, and we can get that from the triangle as well above. Okay. We have tangent of theta. Its co-function is cotangent. Okay. And then cotangent of theta, its co-function is tangent. Again, you can look at the right triangle and you can prove this very easily. Okay. And then the last co-functions identities are secant and cosecant, right? So I'll say cosecant of theta is equal to secant of 90 degrees minus theta, and secant of theta is equal to cosecant of 90 degrees minus theta. Okay, so now we have those co-function identities. Any questions on that? All right, so let's do a quick example here then. And so in this example, right, it'll be phrased kind of like this. Find a cofunction with the same value as. Let's see. So for part A over here, right, we have sine of 46 degrees. Sine of 46 degrees. And so we want to find a cofunction with the same value as sine of 46 degrees, right? Well, we know that the cofunction for sine is cosine, right? And so we're wondering, well, what angle does cosine need to have in order for it to give us the same value as sine of 46 degrees? Okay. Yeah, we want to know what angle do we have to plug in over here, right? Put some red question marks over here, maybe. Okay. All right. What angle needs to go inside of cosine in order to give us the same value there? Okay. Yeah. Oh, it says find a cofunction with the same value as sine of 46 degrees. Fair enough. All right. So we can use our cofunction identity here, right? And so sine of theta, if we let theta be equal to 46 degrees, right? Then cosine, our input for that needs to be 90 degrees minus theta. So let's find out what 90 degrees minus theta is. So that's 90 degrees minus 46 degrees, which will be equal to 44 degrees, right? Yeah. So then sine of 46 degrees is the same thing as cosine of 44 degrees. Okay. So there we have it. Okay. Any questions on that? Any questions at all on that? Scroll up. Okay. All right. Let's do the same thing, but in radians instead, right? Some practice here, right? So let's say we had cotangent of pi over 12 rads. I'm going to stop saying rads. It's just cotangent of pi over 12, right? If it doesn't show degrees in there, you can automatically assume that it's radians for the rest of the semester, basically. So cotangent of pi over 12, right? So we want to find a cofunction that has the same value as cotangent of pi over 12, okay? Now we know that the cofunction for tangent, for cotangent is tangent, right? So then we need to find out what angle needs to go in here in order for, why not? Yeah. I hate OneNote. Why do I use it? No thanks. Let's see. Yeah, that's a lot of stuff. Let's go. Okay. All right. So let me write that back down over here. Maybe. Okay. That works a little bit better. Okay. Maybe. All right. Get rid of this. Now, we have cotangent of pi over 12, was it? Yeah. And we're trying to find a cofunction that has the same value, right? And so we said that the cofunction for cotangent is tangent, right? And so we want to know what angle does it need to be inside of here in order for us tangent of this angle to be the same thing as cotangent of pi over 12, right? And so here's our cofunction identity that we're looking at in terms of degrees, right? In terms of degrees there. But remember I said you could replace it with radians. 90 degrees is the same thing as pi over 2 rads. So then cotangent of theta is the same thing as tangent of pi over 2 minus theta. Okay, fair enough. So if we let theta be pi over 12, right? Scroll up a little bit here. If we let theta equal pi over 12, then we'll have that cotangent of pi over 12 will be equal to tangent of pi over 2 minus pi over 12. Okay? And we still need to simplify that, right? So pi over 2 is the same thing as 6 pi over 12 minus pi over 12 gives us 5 pi over 12, right? Getting common denominators, right? So cotangent of pi over 12 then is equal to tangent of 5 pi over 12. So there's our cofunction identity. All right, any questions on that? Any questions on that? All right. So I said this basically. Here's my algebra. Pi over 2 minus pi over 12. That's the same thing as 6 pi over 12 minus pi over 12, right? Getting a common denominator, so I multiply by 6 on the top and bottom here, right? And then now, since we have a common denominator, we can subtract them, right? So 6 pi minus pi is 5 pi. 12, yeah, okay. Here. All right, any questions on that? All right. So now let's talk about some applications of trigonometry. Very briefly here. All right. And this is not all applications of trigonometry, but this is one that only involves like a little bit of algebra skill and a little bit of trigonometry. So here's a definition. Let's suppose there is an observer, which is usually a person. Doesn't have to be though. It could be a camera or whatever. Yeah, anything that has some kind of sensing ability to like sense locations and distances and stuff. So suppose there is an observer who is staring at an object. If the object has a greater altitude, so it's higher off the ground, right? So if it has a greater altitude than the observer, then the angle of elevation, angle of elevation is the angle between the observer, I'll say between the object, the observer, and the horizontal. What is the horizontal? That would be if the observer was staring straight ahead, he'd be looking at the horizontal, right? Yeah, the horizontal is basically the same altitude that you have. So just staring into the distance. Yeah. So let's draw a picture of that. Okay. Draw a little picture here. So let's say our dude is off the ground here. Right. Here we go. Okay. On the edge of the roof for no particular reason. So if he's staring straight ahead here, that's the horizontal. Okay. Now we have an object in the air, right? So let's say it's an airplane, maybe. Show off my airplane drawing skills here. That's not bad. Okay, so if he's looking at the airplane, then the angle that we're talking about right here, that's your angle of elevation. Angle of elevation. Okay. Yeah. Any questions on that? All right. So now, what if the object is below the observer, right? If the object is below the observer, then the angle is called the angle of depression. Angle of depression. Okay. So let's say we have a car down here, right? So maybe this is like street level, right? So let's say we have a car on the road. Okay. Well, that's not bad either. Wow. Okay. So he's looking down at this car, right? So this angle right over here, that's my angle of depression. Oh. Angle of depression. There we go. All right, so we have an angle of elevation if it's above you, have an angle of depression if it's below you. Okay. So now how can we use that in order to find distances? Right, so let's look at that. So as an example here, phrase in a weird way here, right? Citing the top of a building, a surveyor measured an angle of elevation to be 22 degrees. Okay. The transit, which is the objects that the surveyor uses to tell distances, the transit, right, is 5 feet above the ground. Okay. And 300 feet from the building, the base of the building. Okay. So all this stuff is easily measured, right? Because you could just like walk away from the building a certain number of feet, right? Fair enough. Okay. So all that stuff is easily measured. But what we really want to know is how tall is the building, right? So find the height of the building. Okay. So that's our goal here. Find the height of the building with this information given. Okay. So any questions on that so far? All right. Well, then let's draw a picture, right? So we have the ground, right? And then we have this transit device here. It's on a tripod, right? It's got a little camera lens on it, right? And so this thing is like 5 feet off the ground. Okay. So this is 5 feet right here. Okay. And it's looking at a building over here. Okay. Not to scale. Okay. And this building, the distance, the horizontal distance to the base of the building here is measured to be 300 feet. Okay. And then now we have this angle of elevation, right, between the camera lens and the top of the building. So this angle of elevation is measured to be 22 degrees. Okay, so that's what we're given in the problem statement there. Okay. Now, this is of course a right angle over here, right? If we were just looking straight ahead, it would be, since this building is built perpendicular to the ground, right? There should be a right angle right there. So we have a right triangle, right? So we can reduce this entire thing to just a right triangle. Yeah. So here's our right triangle over here, right? Where this is our angle of 22 degrees, right? Fair enough. And then now, right? This distance right over here, let's think about that for a second. Right? Now we want to know the height of the building, which would be this distance from the roof to the base of the building, right? That whole distance, let's call that H, right? Yeah, so that would be H right there. Okay, that's what we're looking for. Okay. Now, we're 5 feet off the ground, though, right? This triangle is 5 feet off the ground. So this distance right here is 5 feet. Okay. Which means that this distance right over here must be h minus 5 feet, right? Yeah. So then this side of the triangle over here is h minus 5, which totally matters. Okay. Fair enough. Okay. So that's what we want to know. Now this horizontal distance is still 300 feet there. Okay. So I have two sides of the triangle. Well, I have a missing side of the triangle, it's h minus 5, right? And I have one side of the triangle, which is 300 feet. And I have the angle of elevation is 22 degrees, right? Okay. So how can we find out what h is equal to? What trigonometric function might you use here? Which one do you want to use? Keep in mind the information that's given and the information that you want, right? Yeah, we're trying to find this basically. Yeah. We're given this, the adjacent side. We're given this, the angle is 22 degrees, right? Yeah, tangent. Tangent's a good one, right? Because that involves the opposite side, which is what we're looking for, and it involves the adjacent side, which we know, and of course we already know the angle. Yeah. Okay, so tangent is a good one to use. Could you use the other ones? Yeah, but then you might have to find what the hypotenuse is, right? In terms of h, and that's not fun. Okay. So, tangent of 22 degrees is equal to, well, it's opposite over adjacent. Okay. All right. And now I'm going to solve for h, basically. So I'm going to multiply by 300 on both sides. 300 times tangent of 22 degrees equals h minus 5. Now I'll add 5 to both sides. So I get 5 plus 300 tangent of 22 degrees is equal to h. So h is the height of the building, and that's going to be equal to this. Now this is an exact answer. Right, that's an exact answer, which I have no doubt that your MyLab math problems will ask you to put in an exact answer first, right? That's what you would put in. Yeah. 5 plus 300 tangent of 22 degrees. Why would you put that in as your exact answer? Well, it's because 22 degrees isn't like a nice angle that we know how to evaluate what tangent is, right? So we can't really simplify that at all, right? Okay. Yeah. So that would be your exact answer. But now we need an approximation. Okay. So h plus 300 tangent of 22 degrees. Let's see how we might get an approximation for this. Okay. And of course, I should have went ahead and pulled up my calculator here. So let's see here. Now, in case it's been a while since you've done anything with trigonometry and a calculator, first thing you want to do is make sure that your mode is set to the right units. We're using degrees here, right? So we have to go over here and we have to go to degrees. So down, down, put it on degrees, press enter. Right now you see how degrees is lit up, right? Yeah. So now we know that our trigonometric functions are accepting degrees and not radians, right? Okay. I'll quit out of this by pressing second in mode. Okay. So then now, right, we want 5 plus 300 times tangent of 22 degrees. No problem. It's 5 plus 300 times tangent of 22. And it's automatically in degrees, right? So we press enter, and there it is, 126.21 feet. Okay. 126.21 feet. Yes. I'll do an example like that in just a second. Yeah. But to answer your question, it's when you're looking for the angle. Yeah. Yeah, that's when you use the inverse function. Yeah. Okay, any questions on that? So I've got one more example for you guys, and then we'll be done with section 5.2. I know it's been like a week, right? We've been working on section 5.2. A lot of good stuff, though. A lot of foundational stuff that if we don't get this now in the right triangles, then it's going to make the rest of the course so much harder. Yeah, okay. So, a building that is 21 meters tall Right? Cast a shadow 25 meters long. Okay, so 25-meter long shadow. Find the angle of elevation of the sun to the nearest degree. To the nearest degree. Okay. So let's just draw a picture, right? Okay, so we have this building over here. Okay. Right, it's casting a shadow on the ground. Okay. So here's our right angle over here. Here's our angle of elevation that we're actually looking for. We're told that the building is 21 meters tall, and that at a distance from the base of the building to this to the end of the shadow over here, right? So this is my shadow over here, right? This is 25 meters. Okay. So we have 21 meters this way, 25 meters this way. Okay. And again, right, we have an angle, we have an opposite side and an adjacent side involved. I swear, every classroom, I think OneNote has problems, so I need to come up with another program. All right, anyway, so again, we have the opposite side, the adjacent side, and the angle involved, so we're going to use tangent again, right? So tangent of theta is equal to opposite over adjacent, okay? So that's what tangent of theta is equal to, okay? Now, what I want to know, it's not what tangent of theta is equal to. Yeah, I want to know what theta is equal to. Okay, I want to know the angle itself. Yeah, fair enough. So I need to solve this equation for theta somehow. Yeah, and so that's where inverse functions come in. And if you've forgotten what an inverse function is, well, if we have a function f of x, right? An inverse function is a function that when we take f of x and we plug it in to f inverse, right? Then they simplify to just give us whatever's on the inside, basically. Yeah. So there's an inverse for tangent on, well, we'll talk a little bit more about inverses later on, but there's an inverse function for tangent on certain restricted domains. So we can take tangent inverse on both sides of the equation, right? Remember, whatever you do to the one side, you got to do the same thing to the other side. Okay, there we go. Fair enough. So all I've done there is I've took tangent inverse of the left-hand side, and that has to be equal to tangent inverse of the right-hand side. Okay? Yeah. For any acute angle theta, tangent inverse and tangent will always cancel off to just give us theta. Yeah, fair enough. Just like f inverse of f of x simplifies to just give us x, the argument there, right? Same thing. Tangent inverse of tangent of theta just gives us theta, right? And that's going to be equal to tangent inverse of 21 over 25. Okay. Okay. Now, I just wanted to give a little notational thing here. Oftentimes I'll write arctangent instead of tangent inverse. Yeah. So I'll write arctangent, which means exactly the same thing as tangent inverse, and we'll go through some justification of why it's called arctangent later on, and that's too material. Yeah. But so theta is equal to arctangent of 21 over 25. Remember, that's the same thing as tangent inverse. Yeah. But now, how do we find out what that angle is? Well, we get our calculator out here. Okay, and you see how right above sine, there's a sine inverse. Right above cosine, there's a cosine inverse. And right above tangent, there's a tangent inverse. So basically, if I click the second button and I click tangent, then that gives me tangent inverse, right? And we want to do tangent inverse of 21 over 25. Now remember, my mode is set in degrees, so the answer it's going to give me will be in terms of degrees, not radians, okay? So tangent inverse of 21 over 25, I press enter, and it's a 40-degree angle. Okay. Yeah. Fair enough. It says round to the nearest degree in the instructions there. So 40 degrees. So my theta is approximately 40 degrees. Okay, that's your angle of elevation to the sun. Okay. So yes, if you're ever looking for that angle of elevation or angle of depression, then yeah, that would be when you want to use the inverse trig functions. Okay. Yeah.